key is you got to hit it quick and short, and you got to hit the pie tan quick and short. If that happens, in theory, the pie tan will hit the paper towel roll out of the way, but the egg has more mass. Hopefully it wants to stay at rest, and we'll see it plunge into the water and go swimming. That's the goal. Try it. Oh my goodness, I'm nervous. Now you gotta hit it. You gotta hit it pretty forceful, but not go too far. Okay. Okay. Nice. I knew I could try it right here. Yeah, that definitely demonstrated one of Newton's laws right there.
Nice.
Okay. Egg drop. Proving Newton's first law. Drum roll, please. Yes! Good job.
Don't screw up.
Yeah, don't screw this up, otherwise you clean up, right? That's a nice natural consequence. Every action has an opposite and equal reaction.
Clean up.
Okay, so I'm going to put this egg right on top of there. Okay, your job. Now, you can back out if you want. So if this sounds too tough for you, you don't have to do it. Okay, your goal is to hit the pie tin so that it hits the paper towel roll, so that they both move out of the way and the egg goes swimming straight underneath it in the water. Okay, so if we know inertia, which one of these has a lot of mass versus a little mass of the things balanced here?
The egg has a lot.
Egg has a lot relative to these two have light and fluffy mass. So if we cause a force to accelerate these things, hopefully the most mass has the most inertia and it will stay put. Ansley, if you mess up, we're going to give Kayla and Andy a chance.
Okay.
Okay?
What am I supposed to hit it with?
You're supposed to hit it with your hand. Now, here's what I've seen happen. If you hit it so hard that you knock over the glass, then you have no chance of winning because the egg is going to break anyway. Okay, so you got to hit it pretty quick and you got to stop short so you don't knock over the glass. Does that make sense?
Wow.
You up for it? Okay, let's give her a nice drum roll. This one's called the egg drum.
Here. This design will not cause any passenger discomfort by restricting movement. Obviously, this seatbelt design will fail completely in an accident because it allows the passenger movement even during an accident. An ideal seatbelt mechanism should block the passenger's movement in an accident. Let's see how to convert the current design into an intelligent seatbelt mechanism. During an accident, the vehicle experiences a huge deceleration or suddenly comes to a halt. A clever mechanism can be designed by making use of this effect.
An object will accelerate in the direction of the resultant force. The bigger the force, the greater the acceleration. By doubling the size of the force, it doubles the acceleration. Also, a force acting on a large mass will accelerate it less than the same force acting on a smaller mass. By doubling the mass of the object, it halves its acceleration. The relationship between these variables can be shown by the equation F equals m times a, where F is the resultant force in newtons, m is the mass in kilograms, and a is the acceleration of the object in meters per second squared. For example, if a car has a mass of 700 kilograms and the driver pushes the car with an acceleration of 0.05 meters per second squared, then the force applied was 35 newtons. You can also use the formula to work out the acceleration and the mass. And to leave you with a cool fact, a newton is approximately the weight of an apple.
I will hurtle along behind the building. There's a huge force of the cylinder on the gas. And then that gas pushes back on the cylinder and on me, accelerating me. So
4, 3, 2, 1.
The ground pushes on you. A swimmer pushes on the water pushes back on the swimmer. A hammer pushes on a nail. The nail pushes back on the hammer. At a rocket launch, the rocket's weight, yes, weight is force, is pushing on the ground. And the ground is pushing back on the rocket, an action-reaction pair. And on liftoff, inside the rocket engine, all the combustion gases are igniting, pushing on the rocket. And the rocket is pushing back on the gases with a force equal in size, but in the opposite direction. Another action-reaction pair. It is this rocket combustion gas action-reaction pair that will cause liftoff, as well as the movement of the rocket into space. So let's go back to the bow and arrow. What are the action-reaction pairs at work here? There's the force of your fingers pulling back the string, and the string and bow reacting by pulling back against your fingers. When your fingers release the string and the arrow, the string exerts a force on the arrow, pushing the arrow forward. The reaction is the arrow.
Flippin' physics.
And let's watch that one more time so we can pause it right here. To understand the basics of how this water rocket accelerates upward, please recall my demonstration of throwing a medicine ball while standing on a skateboard, and my demonstration of throwing the same medicine ball out of a canoe. In those demonstrations, the medicine ball moves to the left with negative momentum, and the skateboard and I, or the canoe and I, move to the right with positive momentum. This is because momentum is conserved when I throw the ball, because the force I apply on the ball is equal and opposite to the force the ball applies on me. In other words, all the forces are internal to each system, and the net force on the system equals 0. The same thing is happening here in the water rocket. Air pressure inside the rocket is pushing individual molecules of water out the bottom of the rocket. All forces are internal, momentum is conserved. The water molecules have downward momentum, and the rocket has upward momentum. Each water molecule is just like a microscopic medicine ball being pushed downward by the rocket, causing the rocket to move upward. That is how a rocket